Welcome to the next in our webinar series with Steve and Dave, who are going to be talking through on how we identify the habitable environments in our solar systems. Easy for me to say, as they say. Just a couple of announcements. As before, the white paper, the concept document, is currently in read-only mode, and that will be flipped over to comment mode as soon as the presentations are finished. The other thing is, for anyone who might be listening to this just in audio, or who comes along and watches this later, the slides for this presentation can be accessed directly from the event on the Astrobiology website. So you go to today's event, click on that, and you'll see a link directly to the slides on that. And again, if you want to go back to any of the previous webinars, each of the events is now linked to the recording of the webinars. I think we're running 1 week behind, but those will all gradually catch up. And the process for today, just in case we've got anyone with us who hasn't been to one of these before, during the presentation section, we're encouraging everyone to use the text chat box if you have any points you want to make or questions that you want to raise, and the presenters will pick them up as long as it doesn't derail where they're going at that time. Once the presentation is finished, we'll be encouraging you to use the phone lines to ask questions. If we have a lot of people, and I see the room is gradually filling up, then ideally, if you can use the hand-raising mechanism, which you'll see, I always get this wrong, sort of up at the top of the screen that way. If you notice, as I click on it, it raises the hand next to my name, and that just lets us call you off in order and keep some semblance of order around the way we go. Okay, and with that, I will pass over to Steve.
All right, thanks everyone for joining this discussion. Dave and I will try to present this subset of a larger discussion, and leave lots of time for conversation at the end. So this specific topic is how can we identify habitable environments in our solar system, and we're viewing this as encompassing a lot of planetary exploration in general. And I'll just give a reminder of some of the background. This is based on a lot of brainstorming that has happened within the last few months, and a lot of that occurred at a meeting in Wallops Space Flight Center, our flight facility, in June. And this is a list of some of the people who are involved on site and virtually, and many of whom have contributed since. I'm sure some of you are looking at the document that has emerged as a result right now. And if you can look at older versions of the document by looking at a revision history, and you can see some of the original material that fed into this condensation that Dave and I have largely put together in the last few weeks. So this particular document comes about at a request to reorganize things along the themes shown here. So these are the documents that you'll see online that we're covering in the last week and this week. So the present document about habitable environments in our solar system fits with broader questions of how do habitable systems form, how can a world generate life, and how do we search for life in the solar system once we understand habitability and where it occurs. And beyond that, how do we extend those questions to habitable planets and the search for life beyond our solar system? All right, so those original documents that I mentioned that came about during that Wallops meeting are titled, as you see here, covering the search for life on other worlds in the solar system, how we would remotely find and identify inhabited planets, where on Mars life could have emerged, where it could exist today. Questions as specific as a focus on perchlorate as an electron acceptor for organisms. So you can see there's an emphasis that emerged based on the interest of the people who contributed to the document. There was a group of people who were interested specifically in Titan as an astrobiological target. And there was another group that was interested in trying to ask a broad question of how can a world generate life, and how we can characterize and understand those worlds. So there's both a specific aspect and an effort to generalize to processes. And so we'll try to be faithful to the specific questions that came about in those individual documents, while also trying to group things into processes. Okay, so looking at the thinking that emerged from this exercise, we were led to identify some starting questions, basic questions of how planetary exploration can inform our understanding of where life could occur. Basically, we need to understand habitability first, and we need to ask questions about, specifically in the next decade, but as science progresses in general, what measurements and models are needed to constrain our definition of habitability. And as we explore the solar system by all the means that are available at our disposal, how can we understand habitability in that context, both past and present, in the context of planets and objects that we're observing? My definition of planet is pretty loose. I'd be interested in discussing what people think of when they think of the objects that should be included in this discussion. But generally, the idea is to be very open and to think about all the different questions that we should really be asking, specifically in the next decade, when it comes to looking for habitability in the solar system. Okay, so the documents that were the source for this material inevitably touched on different modes of exploration, and so we thought it would be useful to organize things loosely in those terms, specifically what we can learn from remote sensing that's both ground-based and orbital, by looking at the broad characteristics of objects of interest, mapping environmental indicators, and this can be viewed as having a feed forward to the other mode of exploration that follows that in this list, which is in situ exploration, getting down to detail and asking some similar questions, but inevitably with a different set of tools at our disposal that allows us to address those questions in unique ways. Similarly, there are examples of sample return within the solar system that have yielded important answers to questions about the origin of the solar system, and sample return figures heavily in considerations of where astrobiology is headed. So that's something that we want to include in the discussion, and that certainly figured into the documents that were the source for this material that we're discussing today. So the first of those themes, remote sensing, habitability, and indicators. If you look at the document, I imagine a lot of you are looking at the document online right now. A lot of the questions from those source documents ended up in this remote sensing section. Now, that's not to say that a lot of those questions don't also apply to in situ or sample return. And really, the document might be reorganized so that the introduction touches on some of those questions. In any case, some of the themes that come up in the context of searching for habitability in the solar system, which are broadly addressed by remote sensing, are determining global and regional scales of processes, asking what are the inventories of resources that are related to habitability, and again, that relates to future, more specific investigation. As an example, we want to do, or one should be interested in getting high-resolution maps of our surface in order to understand where to look for habitability. And my view is that in future exploration, one needs to get down below the meter scale to understand where processes related to habitability occur. Okay, so specifically when looking at what those environments are, we want to look for the materials that are related to life. And our understanding of life is that solvents are required for fostering chemical disequilibria. Specifically, water has a strong role. We're all, I'm sure, quite familiar. So we want to look for evidence for water, understand the duration, lifetime of water, and what are the subsurface reservoirs of water, be they on Enceladus, Europa, Mars. Potentially even water on the moon is important in the context of habitability. So in general, we're looking for the ingredients of life in the solar system, and this is familiar ground, looking for carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, looking for key chemical signatures. Okay, so these are the broad things, sources of energy, both solar energy and also internal energy, and also processes that might drive chemical disequilibria. And then asking what are the processes that either destroy or preserve those signatures of habitability? Okay, so these are some of the things that have emerged from considering the broad input. But specific questions that were raised in the source documents that are captured in this remote sensing section were, what's the nature of water-rock interactions on different objects? What are sources of water and gases that are observed? In the examples that were raised were Mars and Enceladus. But generally, where we find emissions, what are the sources for those? And what are the processes that preserve or alter those again? And touching on chemical energy sources, there were specific questions about oxidants on Mars, again, perchlorate. In the context of Titan, what is the source of oxygen for putative life forms? What are the sources for reductants in general on different objects that might be habitable? What are the internal sources of energy? What else? And again, what's the distribution of habitable environments? Okay, and so for these modes of exploration that we identified, we wanted to provide examples of past and future missions that are slated to be launched that contribute to addressing these questions. And we wanted to cast the net very broadly. So in the category of remote sensing, I include the Keck telescopes as an example of ground-based observatories that can be used and have been used to address questions related to habitability. There's a host of other missions, Mars missions, the Voyager, Galileo, Cassini missions, and missions in the future that are listed here. This list is not meant to be comprehensive, and I hope that in our discussion we can touch on other aspects, and also perhaps on missions that have been studied as possible future aspects. All right. Dave?
Oh, okay. I guess I'll take over this part of the presentation now. We're switching now to in situ exploration. So the key role then again of the orbital observations, in addition to documenting sort of global scale process, is to contribute to the Solomonic decision of where do you send a lander to the surface. So whereas a lander has a lot of things it can do by being right up against the surface in terms of observations in detail, it is very hostage to your global perspective and your best guess as to the most promising places on the surface of any object. And so you can see how these two modes of exploration really have to be done in concert with each other. But once you're down at the surface, what you're seeing here is a whole checklist of features that a lander or rover could investigate to really characterize the current environment as well as the past environment. And so part of this is to put out to the astrobiology community the types of measurements in a very generic sense that represent opportunities for this community to utilize to do the kind of characterization that they feel is important to address this issue of habitability, not only whether it existed, but how long it persisted, as some kind of a measure of the past environment and the prospect that it might have harbored life at some time. So I think without going down this list, I think when you look at it, it's pretty self-explanatory. It really addresses morphologic features, mineralogic features, chemistry, isotopes, all the usual suspects that are not only examples of categories of biosignatures, they are examples of categories of environmental indicators that could inform the decision about habitability. And at the bottom, last but not least, is the whole topic of subsurface environments, and therefore astrobiologists need to think about geophysical and geochemical indicators of the subsurface, as it appears for many of the objects, in particular the icy moons of the outer solar system. The subsurface is a very promising venue for certainly present habitability as well as past. So these are the kinds measurements that the community should be making inputs about as to how missions should be capable as they go forward, and of course, with greatest relevance perhaps to future missions, where there's still a lot of input to the nature of what those missions might be. The next slide, which I have to use doing this.
I got it.
Thank you. Again, example key questions, and again, as Steve mentioned, we tried to pull these from the source text document that have been developed over the last several months. And so obviously some of these are recognizable again and similar to what we saw in the remote sensing section. And that is, of course, what are the major lithologies at the surface as indicators of the types of ingredients and features that are needed to support habitability. And obviously Titan, Europa, and Mars are going to be quite different objects with respect to those lithologies, and those crustal compositions really provide a context for any habitable conditions that we would be able to get direct access to. And of course, to the extent that surface materials give a clue as to what's in the subsurface, perhaps because of some kind of an eruptive event or something, they also give us to proceed with subsurface exploration. Water-rock interactions, Steve already mentioned, sources and sinks of things, obviously, inventories, all the usual stuff. Organic matter, now, of course, that you're at the surface, you have the ability to do much more about detection of organic matter and characterization of it. And we're not just talking about organic matter as an indicator of life necessarily. In the case of an object like Titan or maybe Europa, organic matter could tell you a lot about the processes, sort of large-scale processes that are related to determining habitable environments. And of course, obviously, organic matter in itself is a source of a key ingredient potentially to any life form that might be there. And so, likewise, oxidants, reductants to address the energy aspect, and then just general conditions. How saline or fresh is the water, and how does that comply with our concept? How does that interact with our concepts of what is required for habitability? Temperature, pH, radiation, all of these things contribute to an assessment of habitability. And I just want to make a few more comments about this idea of preservation. It's not just enough to think that you've landed at a place where that might have been habitable in the past. What you also really need is to have materials that you can then access with your spacecraft that really will inform you about more details about what past environments or even present environments might be. And so preservation is really an important thing here. It's doesn't just apply to biosignatures, it applies to any indicator of an environment that is remote from you, or either because of time or because it's in the subsurface. We need to think about these landing sites and think about measurements that really help us to assess the materials that we are able to observe with respect to how well they have preserved the information that we're after. And so this applies not only to biosignatures, but to indicators of past conditions, with particular emphasis on habitability. And so I think this concept of taphonomy, this is a word not familiar to some of you, is just the relationship between it's a biological term, the relationship between the living organism and its fossil equivalent preserved in the rock record. What are the changes that happen? How can you look at the fossil and relate that back to the original organism? That whole area of study is called taphonomy. And so in a way, maybe we should be talking about a taphonomy of environmental indicators. How does this indicator that's preserved in front of you as you're in your spacecraft, as you're looking at it, how does that relate to the original environment that you're trying to understand? So this is an important part of planetary exploration that we're really now beginning to realize, I think, particularly in Mars exploration, but given the radiation environments of the outer solar system, I think it's also relevant. Okay, so with this, measurements and capabilities, again, I don't want to dwell on this too much. A lot of this, of course, is heritage from the rovers that we have sent to Mars, but any spacecraft you send to the surface of any object in the outer solar system or whatever probably will involve these sort of generic measurement capabilities. And so in the context of these various objects, the astrobiology community needs to think about, what progress is needed in the development of measurements, techniques, instruments for spacecraft that will not only make the measurement, but that can be accommodated within the resource constraints of that mission. And it's not just the size of it and the power capabilities of the spacecraft, but as you can imagine, these days it's the budgetary constraints. How can we address this list effectively given all these constraints on spaceflight instruments and achieve the astrobiology objectives that we need? And not to ignore, of course, at the bottom of this list, the issues of mobility and sample acquisition. These are expensive items, and the question again to the community, if you wanted to explore the surface of Titan or Europa or whatever, how do you contribute to a science definition team that was trying to come up with a design for a spacecraft? And so the community needs to make inputs along these lines as well, in terms of in the context of the science that needs to be achieved. And so I think we go to the next slide, the themes. Okay, now, so that's pretty much it for In Situ, and I think as some people have already commented, there needs to be more questions, science questions, and specific science investigations as examples of the kinds of things we would like to do in landed missions. And so I think Steve and I were pretty faithful to trying to pull things out of the source documents for this to populate this template. But we obviously want more input from folks now that they see sort of this landscape of things that need to be addressed. What could be some more example questions of astrobiology investigations that would be done at the surface. If you somehow see what's already here is not adequate, that would be great to have more input. Okay, the last major theme. Now, did you want to address this, Steve, or me? It's your call. Oops, you're on mute.
You seem to be muted.
Okay.
Sorry, my gesturing was sufficient to say I'm okay either way. But yeah, Dave, I thought you might have some particular perspectives on this, so please feel free.
Okay. Well, certainly for Mars, there's been this progression from remote sensing to landed missions, and then the planning to try to ultimately bring samples back. And I guess the key point is that perhaps some of the questions that astrobiologists want to ask just really require state-of-the-art laboratories to address them. And I think, part of the discussions that I've had with Steve, and maybe also that have been in some of the discussion groups, has been that already for the outer solar system, where you're trying to understand the origins of volatiles and just the materials that comprise some of these objects, that this whole issue of origins is really important. And so therefore, missions like Genesis and Stardust and Hayabusa, basically bringing samples back from very primitive objects is a very important perspective on understanding the origins of these bodies. And so even for the outer solar system, sample return is playing a very important role. Clearly, in the case of Mars, that's yet to be achieved, but some of the reasons for doing sample return are outlined here. And the key point here is that you're bringing together suites of samples that were carefully selected from known environmental contexts. And this is the one advantage that a sample return from a big object has over a meteorite that landed in your backyard, or in Antarctica for that matter. You can go to the object and in a known environmental context, choose the samples you want, as opposed to the samples that Mother Nature delivered to you in the meteorite, and then bring that into state-of-the-art laboratories. So it's in a way an optimization of two worlds: good sample selection, state-of-the-art laboratories. So that's the core principle of sample return. And then, of course, as I just said, for primitive objects, interpreting origins and compositions of planetary bodies for Mars, characterizing environmental indicators in greater detail, and, of course, confirming any biosignatures is a strong conviction in the Mars community that you really need to get to state-of-the-art laboratory capability to really confirm a biosignature. And for that, I can only offer you the debate of the Allen Hills meteorite, and how even in state-of-the-art laboratories, there were some very contentious and unresolved issues for quite a while. Ability to respond to unanticipated findings by employing additional measurements and developing new methods, and that is the idea, the ability to adapt to a finding that you did not anticipate when you return to that sample. And of course, all of this involves planetary protection considerations. So the key thing here to the astrobiology community is, for all of you with your laboratories on the Earth, with your capabilities and so forth, what is your role really in moving astrobiology forward in exploration of the solar system, assuming that you could get samples back and actually analyze them in your lab? What is it what are the capabilities that we need to develop? What are the key questions that really require sample return? And of course, that is a way of putting science in the driver's seat to push for sample return in areas and in examples where the astrobiology community thinks are most appropriate. So that's really the gist here. In a way, this is very forward-looking because obviously most sample returns are in the future, and we need the community to sort of weigh in on the importance of it. So with that, let me hand that to you, Steve, just for your wrap-up.
Yeah, so I thought it'd be useful to put in one last slide just on where this document might go. Again, this is meant to be open, and I view the real value of this document as drawing in as much of planetary exploration as possible to ask what are the important questions about habitability we should be asking in the coming decade. And that's certainly not meant to advocate for one mode of exploration over another. I definitely resonate with this Dave's comment about what types of measurements are needed and could be possible in the coming decade. So, I suggested in this first bullet that one might include perspectives on trends of instrument development, including measurements that might be possible in situ or from space in the future, maybe that aren't available now. The other aspect is what other objects should we be including that aren't discussed here? Again, there's an emphasis on Mars, Europa, and Enceladus, Titan that kind of comes through just on the basis of what was contributed. And I threw in a last question that was just meant to be to provoke a real breadth of discussion. What's the role of human exploration in all this? So with that, I'd like to just open it up for discussion. We've got some questions coming in already.
Should we take Alex first, because Alex's hand is in the air?
Andy, you are very staticky. If you're coming in voice over IP, you may want to hang up and just redial.
Okay, thanks.
But Alex, are you on the telecom line? You can ask your question now.
Yes. So, can everybody hear me? I heard static. A lot of static.
Yeah, you're good.
Yeah, you're a little quiet, so you speak up a bit.
All right. So, I think astrobiology community should reopen debate about looking for extinct versus extant, searching for extinct versus extant life on Mars. I mean, the strategies which are outlined and the requirements are completely different, and it seems like from the side, but by not participating in this decision making, that there is a kind of a implicit going with looking for the extinct life, searching for the ancient biomarkers and going for places where the ancient life could have been, and that's focus of curiosity and of Mars 220, and eventually will become of Mars sample return. I believe, from my opinion, that we need to step back a little and actually look is that exactly what we want to do, because there are certainly very strong arguments against. And radiation is primary one against against preservation of anything complex in the top centimeters of Martian soil where we're going to sample. So that concerns me, that we don't even debate that question, that we are just implicitly going for the extinct life. Thank you.
I can read.
Yes. No, go ahead.
Well, two things. One is, if you had life someplace a million years ago, and now you're looking at the remnants of it as biosignatures, even though you're using past life methods, you're actually looking for evidence of extant life, because I would argue that any evidence of life that was around in the last few million years, it would be evidence that you have extant life on Mars. So a lot of the past life methodologies, I think, are relevant actually to extant life searches, recognizing that where your spacecraft is sitting at the moment might not be habitable, but if it was habitable in the last million years, or if it reflected materials from a place that was habitable in the last million years, you're essentially doing an extant life search and making progress on that. But I think another key point I should make is that I think a real challenge to people looking for extant life on Mars is to come up with how do we do the spacecraft. I mean, if you want to go to a high polar latitude and you want to drill down into the ice, how is that spacecraft going to last long enough to do that drilling? Or how is your spacecraft going to really be effective at detecting subsurface environments? And so I hear you, Alex. I think it's a very important topic that deserves more emphasis. But the community really has to start thinking about the realities of a spacecraft surviving on the surface of Mars and incorporate that into a plan or a recommendation. Another one is these recurring slope lineae, very exciting potential examples of fluid in the modern Martian environment. But these are very challenging places. They're on slopes that are unstable, and engineers just get nightmares about being told to drive into one of those environments. And so how do we actually do the surface exploration in some of these places? So not to try to say no to any of this, but I think these are the examples of the challenges that the community has to begin to address. So I agree, it does need more attention.
So I'm hearing sort of bullet point questions and Alex's questions or point that might be incorporated into the document, which are what are the best places, specific places, I guess, landing sites on Mars that one would go to look for habitable versus previously inhabited environments?
Yeah, I mean, just to be more specific, I just wanted to clarify. You bring in point that if something was out for a million years and now it's no longer alive, then you can use the same techniques. Yet, for example, the state of hydration of the rock, it might be deadly for preservation. While if you're looking for extant life, you want to go where the water is. So debate needs to be still there to clarify, but particularly in applications for the future landing sites. That's all.
Yeah, well, please send in some questions that sort of frame some of this stuff, because I think it really would be important to try to put some of these challenging questions into the document. Okay, Steve, did you want to go down the list of stuff that's been in the chat, or?
Sure. Yeah, I wanted to say, with the idea of adding to the document, if you wanted to put in your bullet point questions either in the chat or in the document itself later, or I don't know if it's open now. That'd be great. So. Just going down the open chat, Brittany Schmidt writes, miniaturization is definitely something we should be thinking about. I think definitely, where instrumentation is going in the next decade is an exciting question to ask about. How the types of questions we can ask will change during that time. Right, and Brittany also raises the point, or suggests we're not going to be able to return samples from everywhere, but we can send more sophisticated instruments outward. I guess that's a comment about maybe the breadth of science that might be returned from focused exploration missions versus the level of input needed for sample return.
You just made a comment about Brittany's second comment there about sample? Yeah, I think something to think about here. Given that, as you can imagine, there's a lot of uncertainty about which objects are going to be higher, next ones being addressed, and the politics of it all and everything. But one thing that could be generic that would be worth thinking about is just instrument development. One of the reasons I've put that list of measurements in there is to think in terms of generic measurements that would be useful at a number of destinations, and that if the astrobiology community advocated for some more development in some of these by whatever means, that would be a good investment regardless of which missions turn out to be highest in the queue. So instrument development doesn't necessarily have to be target specific, and figuring out how to prioritize and advocate in a way that you're always ready for the key mission when it comes along, I think is a key part of the strategy.
Just in case anyone didn't see the comment I put in the text box, the document is now open for commenting. So if you want to, just in case anyone hasn't done it before, the process is you just highlight a piece of text, choose comment from your right-click menu, and you can stick the virtual post-it notes on there.
Okay. John Rummel made a number of comments. I don't know, Steve, have you read those? Let's see.
I think let's see. The first one John made was 2020 mission will be the first in a trio that could bring people back to Mars. That's kind of in line with what you were saying, Dave, about where Mars exploration might be headed.
Yeah, well, the key point from John is, science or not, any sample that comes back will be looked for present-day life for planetary protection requirements. So, but again, getting to Alex's point, where you pick that sample from certainly will affect, the probably have an effect on the probability that extant life would be somehow reflected in that. So there's a selection of sample thing that that might weigh in. But in any case, all samples will be checked for extant life as a requirement. So let's see. And he says giving engineers nightmares is not a bad thing. Sometimes it's required. Well, okay.
Well, especially when you want to bring back a sample that's clean enough to be looked at for non-Florida life.
Yeah, there you go. Exactly. Okay, an additional perspective tying in elsewhere. John, do you just want to comment to it since you're right there?
Yeah, it's just that, oftentimes we think about habitable zones as places where we would be comfortable. I think that we tend to, even though we shouldn't, neglect sometimes deep sea type organisms and other kinds. And if you look at where organisms might be formed in an origin endeavor, they may be at these highly energetic and very episodic kinds of places, but where life proliferates and maybe in greater abundance could be places where you could never actually have an origin of life, but are nice, materially sufficient and energetically available type places like a warm little pool. So I do think that there's a tie-in to the origin of life group because something that might be challenging but habitable, say a deep aquifer on Mars that's exposed to some of the latent volcanism, might not be the place to go looking for Mars viruses, for example.
Yeah. This reminds me of another key perspective, and that is that the role that the characterization of a habitable environment has in supporting the detection of biosignatures. And what I mean by that is that if you have a habitable environment, or as John was talking about, an environment in which life could begin, you're probably talking about an environment that's going to create a lot of features that might mimic biosignatures. And so in a way, that establishing something as a definitive biosignature is an exercise in signal to noise. The signal is the life-created feature. The noise is all the other stuff that environment creates as chemical or mineralogical background. And you have to resolve your biosignature signal against that habitable environment noise. And so just as a process of detecting biosignatures, you've got to characterize your noisy background. And of course, if you're talking about a place where life could begin, you're talking about a place where a sequence of events is leading up to life, and that's a gray zone between the non-living and the living, and we've got to be prepared how to navigate that. So what kind of organic chemical measurements do you make? What types of observations do you make to sort of help you figure out, what the sources are of all these interesting features that you're going to be confronted with? So I think
we're so good at defining where life starts too.
Right, exactly. And so, part of this is something that can get you very enthusiastic about making organic chemical measurements because, as we all know, organic chemistry is so rich in its information content that it's a great indicator of process. But at the same time, it's also challenging to interpret, and sending instruments to other planets that can really get into the details of organic chemistry. These are complex instruments, and I think certainly for Mars and probably for all objects, a big challenge for the astrobiology community is how do we get more effective at organic detection and characterization in missions.
Jen Eichenbrod and Sean Goldman raised a couple of, I think, related points. There's a nice discussion going on about how in-situ exploration on Earth could inform the types of more comprehensive investigations might be needed. I'm just trying to summarize here my understanding. Sean's point is you consider either in the context of exoplanets, which are even harder in the search for habitability, but think of an ice-covered world like Europa or Enceladus. If you're looking for surface communication of a signature of habitability, you're presented with challenges of understanding how those signatures evolve, but also how to make the suite of measurements that will be necessary. to understand habitability in that context. I think that touches on the same kinds of issues of organic detection that Dave was describing as well.
Yeah, so I mean, a key point is that organic matter can be a wonderfully detailed environmental indicator, but the astrobiology community is really the only community out there that is advocating strongly for organic measurements in spacecraft at the moment, and so there's a key niche that the astrobiology community could provide for the planetary exploration. And, you know, organic chemistry, especially in the outer solar system, is just an indicator of process and environment.
Do you want to take any of these text chats onto voice? Oh, we just lost Steve.
Oh,
you just lost it again.
Yeah, my video just reset for some reason.
Well, let's see. Jen, you made quite a comment there. Did you want to explain that?
You're referring to my comment, Dave?
Well, yeah, anything you want to say. You're making a lot of comments.
Okay. Yeah. One was, in the big picture, you know, when we go to a planet, we have a limited set of instruments, and we have a limited amount of time, resources to study whatever it is we've gone to study. We have specific questions outlined. Everything was tailored towards that. But in the big picture, that planetary in situ science has severe limitations in comparison to what we do on Earth. Now, on Earth, we go to the field or we do something in a lab and we can sample, you know, to our heart's content and make analyses that are made on a variety of instruments, as many analyses as we want, and on instruments that have higher sensitivity. There is a complete disconnect between those two types of science approaches. And I think that planetary in situ science would strongly benefit from people doing the comprehensive studies on Earth and reflecting at what a high-fidelity planetary in situ science would have provided as far as information goes and how we interpret that. And it's something that it's challenging to do, and people have to do it very deliberately.
So a nice example of synergy between Earth-based and research and mission development.
Yeah, another thought I had was, and this is this kind of stems from my own PhD research, is that you know, we are so spoiled by Earth's biosphere. We're surrounded all the time. We have life everywhere. We know what the biosignatures are. When we talk about extraterrestrial life, we don't know what those biosignatures are. We're taking a guess based on Earth, and perhaps those aren't going to be the right ones. And so, in the long run, unless there's some Martian out there waving at us saying hello, I'm not so sure that a biosignature is going to convince us that we have evidence of extraterrestrial life. We don't know yet. It depends on what we find. But the thing that is so unique about life is it's part of this ecosystem, and it has interactions with the rest of the environment around it, and it leaves a record of that in both the extinct as well, the recorded as well as the extant environment. And so perhaps the way we will convince ourselves of the presence of extraterrestrial life will be to understand that ecosystem or the record of it. And so this is very much part of, I should say, the approach that we have been taking to planetary science, I think, fits this, but it was never motivated by this idea.
So in a way, I mean, one thing you know you can do is go to an object and begin to characterize the past and present environment there, and you just keep characterizing it. You have a model about the processes and so forth that are involved, and you just do that, and at some point you suddenly start coming up with features that you can't explain by your model, which is basically based on non-biological process. And of course, and this is the way to be perhaps most objective about confronting the possibility that you've got a biosignature, because the definition of a biosignature is something that requires a biological process. So if you can't explain something with non-biological processes, you might be onto something here in terms of your search for a biosignature. So again, the search for biosignatures, in my view, goes through the neighborhood of characterizing the environment, the extent to which it might be habitable, and then having a model to explain what you're seeing, and then as you move forward, you may or may not be getting closer to detecting evidence of life.
Yeah, well, and I think there was a request to split this into two documents, focusing on habitability and also on life detection, because habitability is such a broad issue. It's something we're really trying to understand, and planetary science has a huge set of tools that can allow us to understand the chemistry of the solar system, the origin of the planets, things that have a long progression that goes from chemistry not directly related to life to eventually creating the conditions that can lead to habitability.
Okay, Sean made a key point, and I think I want to respond to that, but let's see. Sean, why don't you, can you put your comments into words, and then...
Yeah, I mean, I think you guys have been making great points, and I don't want to imply that you weren't, or that you were suggesting this, but I just want to make sure that we also have space in the document for research that isn't directly tied to near-term measurements, right? We need to do that so that we provide the motivations for measurements further out on the horizon than the next decade or 2 decades. And sometimes we need things that will never be measured to provide context for the measurements we can make, and to just do the fundamental science of how these planets operate and how life might operate or have operated on those planets. Sometimes these things just aren't amenable to measurement at all, but we should still be doing them, not just as an agency, but as a community.
Yeah, two responses. I absolutely agree with you that this should not be a focus only on near term, that we should be looking at it far term. But at the same time, this particular topic that we're discussing today really is mission-oriented. And I think that's what differentiates it from some of the other topic groups which deal with like basics of habitability and all of that. This is really applying astrobiology to missions, although I totally agree that it should be off into the future as far out as we can conceptualize, just to keep it open in that respect.
Dave, do you see John's point just in the chat window?
John, you want to verbalize that?
Just that we're looking at special regions on Mars as potential habitats, and so looking forward to putting together an effort that will update the definitions and possibly do a better job of locating features that might lead us to believe that those special region definitions could actually be inclusive at those places. So RSLs, for example, you already mentioned, but those are places where there may in fact be liquid water at cold temperatures with a large briny content. And then the question is, is there an Earth organism that can live in there? We don't define special regions on the basis of Martian organisms, but certainly those would be places to look if we were going to go start looking for Martian organisms. But anyway, it's just something that's going to happen over the next year, and I thought I'd throw that into the mix.
Yeah, so just a general comment from me is that planetary protection really addresses legal requirements and some just proper housekeeping that we need to do with exploration. But there is this really, I think, substantive link between planetary protection and the search for extant life, because that's sort of the essence of the phenomenon that both of these topics are addressing. And so there could be some synergy there in terms of future activities.
This is Sean again. Do you guys mind if I just jump in for a minute?
Sure, go ahead.
So I just want to give an example of the type of thing I'm talking about with maybe non-mission solar system habitability topics of research. And this is target specific, and I don't mean to mention this target to the exclusion of other ideas, just as an example. Imagine the hypothesis that there's a potential double biosphere on Titan, right? One at the surface in these methane-ethane organic lakes, and then a second in a deep, deep subsurface water layer. Now, whether or not that deep subsurface water layer is habitable or not, I think is something that we should be exploring as a community of astrobiologists. Even though I don't see any prospects, even in the next century, for testing that with instrumentation. But I don't think we should be excluding that, looking at that from a theoretical perspective, because as a community, we really should be the one. I mean, if we're not going to cover that, first off, who else is? And secondly, if one of the goals of astrobiology is to put together a list of all the places that alien life might crop up, that's one of them. And we should be exploring that as rigorously as we can without, a super drill going to Titan and going down to that second potentially habitable layer.
So let me respond to my perspective. Sean, you're speaking about a topic that's very close to my heart. See my poster at AGU. I want to, in my own work, contribute those kind of perspectives to these documents. But I did view that as falling into the broader category that Brittany spoke about last week of how do habitable worlds form. So I took it as our goal for this presentation to think about how planetary exploration informs habitability. That is, what are the results that we're getting from Cassini, for example, telling us about Titan's interior, like how thick the ice shell is, and how deep the high pressure ice layer would be in the example that you cite. So I realize we're walking a fine line, and I initially wanted to shy away from mentioning specific missions at all and focus just on things that we can learn from planetary exploration.
I think that's okay, Steve. I mean, if it's in another part of the futures network or roadmap or whatever we're calling it, I think that's okay. I just want to make sure that sort of stuff is not excluded. It needs to be part of what we're talking about over the next decade or two and beyond.
John?
Well, there's this whole concern about whether or not a perched ocean can actually support life, whether or not an original life or just continuous, and how dirty the ice has to be before it becomes silicaceous enough to be envisioned as a habitable environment. That's an argument that's used about Ganymede and about Callisto as well.
Sean, it'd be great if you could just send us a question, sort of a comment about, aspects of habitability in the solar system that are not necessarily connected with missions, but, address some of these fundamental principles that would be associated with our concept of habitability. That would be great.
You got it. Steve, I might take a look at your abstract from AG before I put that in there.
Writer is not yet connected to missions.
In the last few minutes that we have, are there any other topics that people would like to raise that haven't been covered so far, or that might be helpful for the authoring team to take their thinking in different directions? That's the sound of everyone thinking deeply.
Well, there's some interesting activity in the chat window, so I think we got to something late here that was very important, and that is to not be so tied to mission queues, but to think in a much more fundamental way about, be sure that we also think in a very fundamental way about habitability and all of its aspects in the solar system.
Okay. If there are no other topics that people want to introduce at this point, let me encourage you to go over to the document and to make sure that you annotate it with anywhere that you think you can make a useful contribution to that. The slides are available. You'll find that there's a link to a Google Doc set of them. We haven't made the slides commentable. They're read-only. We could change that if anyone feels that it would be useful to comment the slides, but at this point we're just trying to limit the conversation to the document, just to make it easy for the authors to have all of their thoughts there. Okay, just have a look. All right, we'll leave John and Sean to chat away in the text box there. Thank you very much, everyone. That was a great and very useful conversation, and thank you to our presenters. The next webinar is tomorrow, same time, whatever your time zone might be. So thank you very much, and hopefully see you then. Bye-bye.
Thanks, folks.
Thanks, everyone.
Thanks, guys.
Thanks.